people. Thank you for the applause. Thank you. Thank you. So I guess just a little about me. I started learning graphics like over a year ago. So I still have a lot to learn too when it comes to shaders, but I think I know enough to give you guys an introduction. So that's what we're doing today. I'm a tech artist for Wax Art as well, the Wax Art team. And I am also doing a lot of, I guess, software engineering on the side as well for the summer, especially. But yeah, that's like enough about me. Let's just dive right into it. So like, what are shaders? That's like the big question, right? They're just programs, guys. They're just programs that rest on the GPU and do GPU stuff. Specifically, GPU stuff that eventually leads to pixels being displayed on your screen. And each shader is like its own programmable step in the graphics pipeline. The three main types that you'll see is the Vertex Shader, the Fragment Shader, and the Compute Shader. But there's actually more shaders than that. There's a lot of people coming in. Should I wait? I'll wait for just a second. But yeah, as I was saying, there are three main shader types you'll use, which is the Vertex Shader, the Fragment Shader, and the Compute Shader. But here is just a standard like graphics pipeline made in Vulkan. And if you're unfamiliar with Vulkan, it's just a graphics API. And you don't need to know this huge diagram, right? It's like a lot to take in. But the reason why I have this like huge graphics pipeline diagram shown is just to like really just nail into the idea that there are a lot of shaders that do different things, right? So there's the Vertex shader here on the left. There's like the geometry shader, which by the way, is not really as popular as it used to be since it doesn't work well on certain GPUs. There's the mesh shader, which is also like gaining popularity these days. There's the compute shader, of course. And yeah, there's a bunch of shader stages you can learn about. And I think just being aware of like these niches are really good to like just being aware of these shaders existing are good because there might be a niche that, hey, maybe you do want to use a mesh shader one day, you know? So like just be aware of that stuff. And I think it's always good to learn more of, I guess. But if that's not your thing, hey, if you don't want to go deep into making pipelines, setting up all this crazy stuff like freaking task assemblers, like you don't need to do all that, right? That's like more reserved for like graphics programmers. Graphics programmers are the people that tend to set up these pipelines. But when it comes to like understanding the graphics pipeline at a high level, it's actually not that complicated. So we have these like basically like 6 steps. You have these raw vertices and primitives being inputted into the vertex shader. On the diagram, it says vertex processor, but you can think of these as vertex shaders as well. And the vertex shader basically manipulates this vertex data and transforms it into new data. So we can generally like input things like positional data or like your normal vectors if you're familiar with that. And then the vertex shader then transforms this into new information, and then that gets rasterized. The rasterizer is basically it's a fixed stage that does this thing that's called rasterization, and it's a big word that really just means we're kind of transforming like these primitives and vertices into these like little blocks we call fragments, and that's basically like a precursor to like pixels. And then we had this fragment processor stage, which is where all your fragment shaders will be. And the fragment shader basically does all the coloring, right? And then after your fragment shader, it goes into this blending stage. And technically, before the blending stage, we have these things called late per fragment tests. And I'm bringing up these tests. If you look at this Vulkan pipeline, I don't know if you can see my cursor, but on the bottom left, we have this little block called late per fragment test. The reason why I'm bringing up these tests is because you'll see it a lot when you're doing like shader work. This will be like stencil testing, depth testing. I'm only letting you know these terms because you'll eventually run into them the more you do shader work. It's not that important right now, but it is going to be important eventually. Um, But yeah, it's cool stuff. What's up? Yeah. Yep. Okay. Oh, that was the wrong thing. I'm working on it. We are so back. Okay. And I know I went through these slides really quickly. So if you guys have any questions, just like let me know and we can like go back. And I know I'm a fast speaker, so um just let me know, okay? And I know there's still people joining a little late, so I'm okay with like going over the slides again as well. And we can like really just double down on our knowledge, I guess. Um but yeah, then there's the vertex shader. And like I said, it doesn't really need to be that complicated, right? You're just writing programs that transforms inputs into outputs. In this case, we're transforming vertex data into new data. And if you look at these GIFs, this is like a catch-all term, like this kind of technique called like vertex displacement, where you just offset like the vertex positions to create like procedural movements in your meshes. So like a common use case that I've seen is like fractional Brownian motion, which we'll touch on later. But yeah, this is like just basic like vertex displacement. And there's a bunch of different types you can do. Um, this is also kind of a lot to take in. Um, but it doesn't need to be that scary, right? So, what's up? Okay, sorry. Um, so this is oh, okay. Let me actually keep the chat up just in case you guys have questions. I don't know what's happening. Somebody's mic is dying, but that's okay. But yeah. So right here is a diagram that you can find on learnopengl.com, and I'll touch on this website soon. But this is like basically just the steps in order to transform the vertices of an object from local space to clip space. And these transformations are done through certain matrices. You'll notice that on a diagram, we go from local space to world space by multiplying the vertices with the model matrix. And then we transform it from world space to view space by transforming it with the view matrix. And then with the projection matrix, we can transform it from view space to clip space. And then clip space will be basically the camera's projections, like your camera's projection, if that makes sense, how it looks from the camera. Um, and essentially, the reason why I had the shader code listed, it's GLSL, which is a shader language, and it actually tells us a lot about how like the graphics pipeline works and how the GPU works as well. Uh, we see this in keyword on the right side, and that's basically inputting position data that we defined. Basically, we're passing it in from the CPU to the GPU typically sometimes. And then these uniforms are basically global. It's a key word to declare our variables as like global, which is like a shared memory state. So um, we're also generally in this code we pass in the model and view and projection matrix from the CPU to the GPU. So like if we go back to the pipeline, right? Um, these raw vertices and primitives, like this raw data information, that's getting passed in from above here, with this layout specifically. Um, and yeah, the GPU can then read this data by using this layout because it tells you the location of the data, which is really nice. And basically, yeah, this vertex shader specifically is responsible for transforming our input position data that we passed in, and then we're transforming it into vertex data in clip space. So yeah, that's like just one basic example. And this is in more of a I guess coordinate system aspect. But generally, you won't be doing these transformations in a game engine because it kind of handles it for you. But yeah, it's kind of cool to know. The next thing to know is the Fragment Shader. So this is where all your colors happen, and um, this is kind of nice though, because this GIF here, you'll notice that kind of dissolves. So like this kind of like dissolve effect, you can actually like achieve this by like passing in like some kind of noise that manipulates the alpha channel of your colors. And that's kind of how you like achieve this dissolve effect. So yeah, I mean, there's not really much to talk about the fragment shader besides it outputs a final color, but the fact that you can do so much with it is like the most exciting part about it. And that actually leads me to my next point is that you can actually learn a lot about lighting. You can sometimes first, this is like a lighting shader, and this is once again GLSL code, and I'll break it down for us. But lighting is a very popular task in graphics, especially with like ray tracing, right? And this is like what we call Phong lighting. It's a very basic implementation of lighting. It's very, very basic, and I think I'm bringing this up because it's really important to familiarize yourself with some of like the terms here. For example, normal. We're inputting normal vectors, and the fragment shader, or really just lighting algorithms in general, use normals as inputs. And your normals are essential for accurate lighting. So if your normals are cooked, guys, so if you ever see bad lighting behavior in your games, honestly, just check your normals. There's a strong chance that's probably what it is. And if it's not your normals, then maybe you mess with the normals in some way, in some unexpected way in your algorithm for your shader. Another term to get familiar with is this ambient term that I have like highlighted in orange here in this code. And what ambient means is like in the real world, unless you're like in a pitch black cave, a minimum level of light will always seep through wherever you are, right? So you're not going to get complete darkness. And this is essentially what your ambient factor is. It determines how dark your in shadow colors are. And then this diffuse factor simulates the directional impact of a light object has on a object. So like this is like the factor that's responsible for determining how bright each of your objects faces in respect to the light source. And in the specular term, that'll be like that shine on your object. So if you look at this diagram, we have this shine, and that's your specular value essentially. And then it's like this minimum darkness, that's going to be your ambience, and then the diffuse determines basically this is in general just a little bright, just a big bright face. This one's in darkness, etc. But yeah, that's the fragment shader. From like a lighting perspective, it can get a lot more complicated, but yeah. I'll actually touch on this ambient thing and the specular thing again later. And I'll tell you why it's important to know these terms. The compute shader is a really complicated one. It's detached from the pipeline, so it's technically not a part of the graphics pipeline, and that actually grants us a lot of advantages. Um, I wonder why my presentation broke. Okay, that's not important. But yeah, so compute shaders, if you're unfamiliar with computer architecture, I'm going to give you like a quick rundown on computer architecture real quick. The GPU stands for graphics processing unit, and the GPU is inside of your graphics card, which is a term you might be more familiar with. Because the GPU was designed for graphics, it excels in processing data in parallel. So you can think of your GPU as a cargo ship that carries like a ton of data at once. And then you can think of your CPU as a cargo jet that doesn't carry as much data, but it does move quicker. So like in other words, your GPU is not as fast as the CPU, but because it can carry a ton of data at once, the GPU is actually more efficient for certain tasks that require a large amount of computations. Like for example, the GPU excels in graphics due to the large number of matrix operations you have to do with thousands of vertices. It's also useful for machine learning, where you train AI models and you have to do a lot of matrix multiplication on large data sets. But basically, what this boils down to is that like your GPU is designed for parallel processing, and all shaders take advantage of this architecture. but compute shaders can be faster as it can make those general purpose calculations without being bottlenecked by the graphics pipeline. So this is what I mean by like, it's not restricted to one stage. It's not. By being detached from the graphics pipeline, it has that advantage. With like I guess fully working with the graphic the GPU. And one example is like making physics-based calculations to update like the position of your particles. And this is kind of what I mean by like general purpose calculations. You can make calculations that go beyond just like rendering calculations related to like a pixel, I suppose. And here we have a bunch of shader languages and resources. Shader Toy is a really cool website. It lets you. The cats are really cool. That's like my favorite thing about it. And yeah, the GLSL category. This is like GLSL is a shader language. And in each of these links below the GLSL, I guess category are a bunch of things. Actually, I don't even know why the Book of Shaders thing is there. The Book of Shaders is just kind of a general resource that you can like, I guess, touch on upon like a lot of concepts. And in the Book of Shaders, it actually touches upon FBM, fractional Brownian motion. And I brought this up again. It's just because it's like a really cool algorithm you can learn. And then there's learnopengl.com. Now, if you really want to like get into like graphics APIs and like learning how to set up pipelines and do all this crazy stuff, then I would recommend touching upon OpenGL as an API first through this learnopengl.com website, which also touches on a lot of like interesting topics that we kind of take for granted as tech artists. For example, one of those like topics we take for granted is like normal mapping, right? How does normal maps, how do they actually work? And you actually get a deeper dive, a deeper technical dive by going through these graphics API websites. And Shader Toy is like basically a way to play around on a website and write GLSL code and just like really just test your shaders and through that aspect rather than like setting up your own pipeline on like a, I guess, like on Visual Studio Code or something like that. HLSL is another language. This stands for High Level Shading Language. Now, I learned it through Unity. If you guys have any other resources to learn HLSL, feel free to link them. Otherwise, yeah, I think Unity is a really good way to like gain practical experience using HLSL because before I used the Unity, I was doing everything in GLSL. And they kind of operate a little differently. Other languages is CG. CG is like the great value version of HLSL. You honestly don't really need to worry about it. It's like basically like deprecated, and it's the same thing as HLSL. It does everything the same, like syntax wise. Like honestly, look, you don't need to worry about CG, but I decided to add it anyways. Then there's Metal, which is Apple's shading language, like for like iOS and Mac OS. I haven't ever worked with that. And then there's Spur 5, which is like some nerdy Vulkan stuff that you honestly don't really need to worry about, but decided to add it anyways. Then there's visual scripting, which I think is really good. I think it's really cool, to be honest. I think there's some downsides of it because you're kind of like restricted in terms of what you can do with it in comparison to like just programming it from scratch. But it does. I do think it's quicker for development, and I like that aspect of it. There is also some overhead to be had with the like visual scripting graphs because it needs to then be converted with like HLSL with like extra code, which has its own issues. But if you really want to max out your performance, then definitely learn how to program it from scratch. But I think using visual scripting as a beginner is really useful. But yeah, there's Unity Shader Graph, which is like, I guess, still HLSL. And then there's Unreal Engine 5 Material Editor, which is also HLSL. I don't use Unreal Engine 5, but I Googled it and that's what Google told me. So shader graph parameters. So because I personally use shader graph and I use Unity, I'm going to speak for Unity. Like I said, I don't use Unreal Engine 5. I don't use Blender. And I feel more comfortable talking about these parameters, but it's probably transferable, right? Some like these terms here. Position is, of course, like self-explanatory, and then there's other things like the normal and the tangent categories. These are vectors, and if you look on this slide, we have the normal vector, and this normal vector always points perpendicular to like the face, like it always points upwards at the face. And like I said, this is really important for your lighting. If your lighting is screwed, look at your normals. That's probably what it is. And these tangent and binormals are a little more interesting. They're not as commonly used and not as important as the normal, but they're still really useful. For example, I don't know all the use cases for the tangents and the binormal vectors, but you can actually use the tangent and the binormal vectors to recalculate your normal vectors, which can be really useful for writing a procedural shader, such as a water shader, which, has a wavy motion, and therefore your normals won't, you'll have to recalculate your normals to, I guess, be particular to those waves, right? So you can actually use the tangent and binormal to recalculate your normal, which is really cool. There's also, once again, the fragment shader. You're just passing your color. Your normals are, once again, you can pass in your normal maps into the fragment shader, and what normal maps are is it allows you to basically, if you think about a texture, right? You have a brick texture. Normal maps allow you to simulate how light impacts that texture. So like those ridges that you see on like brick, you can actually use a normal map to correctly, I guess, like reflect those light vectors in an accurate way. Um, there's the metallic / specular factor here in the fragment shader in this Unity shader graph. There's two workflows with Unity's lit shader graph, that's metallic and specular. And both of these workflows deal with specular reflections, but the metallic one is, of course, like for more metal materials, I suppose. And specular, what do you remember what we talked about when we talked about specular reflections? Okay, if we go all the way back, look at this. All right. This is what I mean. Okay. If you learn your lighting, you will be able to have transferable knowledge for, other things, because, basically how other people design their shaders will typically be following, certain patterns, such as, lighting patterns. And with Unity shader graph, you have the position, the normal, and the tangent, the vertex shader. But like if you're writing your own vertex shader, you can technically pass in more variables besides the position, the normal, and the tangents. You don't have to restrict yourself to those three things if you're writing these things from scratch. So that's like another thing I'd like to mention. But for smoothness, if we look in the smoothness, this is what smoothness is, right? So like it mimics the roughness of like your surface, and depending on how rough your surface is, it reflects the light vectors in different ways. So, or redirects them, whatever. Then there's the emission, which will be your color and light intensity emitted from the surface. So like emission is really useful for if you want to make like VFX that has to deal with like fire, right? So like if you want like a glowy effect, emission is like your friend. Okay, this is going to be like your go-to thing, especially if you like combine it with like HDR. It looks really nice. And ambient occlusion, ambient. Let's go back. Let's go back. Let's go back. Ambient. Remember ambient? Okay, that's our friend. Okay, the minimum level of like light that like seeps through even in like the darkest of times. Ambient occlusion defines what is occluded or hidden from ambient light. So remember when I brought up that analogy of like a pitch black cave where there is truly no light? That's kind of like the concept of ambient occlusion. It defines what part of our object is truly hidden away from that ambient light that exists. And this is actually like, I have this disclaimer here that is per material and not SSAO. And what SSAO stands for is screen space ambient occlusion. So there's this per material like ambient occlusion implementation, and then there's the screen space ambient occlusion, which is a post-processing effect. And post-processing effects happen. It's one of the latest things that you'll have in your render queue, which is another term you should get familiar with, or render order, because how your pipeline, especially with game engines, how your pipeline handles like transparents and like your opaque objects are different, right? In terms of the order they get rendered in. So that's like something you really need to be aware of. I see you typing, Patrick, so let me know what you think. And finally, I have some examples here of what you can do with shaders. Okay. I can't lie. I never truly understood why ambient occlusion was called ambient occlusion. I just had a brain explosion. I am glad you're learning things from this. Okay. But yeah, here's some cool things you can do with shaders. Foliage is a really good. It was actually one of my first introductions to shaders. It really teaches you things like methods of like vertex displacement and potentially color techniques. But I think this is like a really good example of vertex displacement because you can like mimic wind for your leaves, right? If you displace it with like noise. Tune shaders are a good way to like, I don't know, play with the fragment shader. Yeah, Makai was actually the one that got me on the foliage shader train. I was assigned to do that by him. So shout out Mikhail. That's a real shout out. Post processing effects. So are they're in my opinion an awesome way to further your understanding of the graphics pipeline. It taught me so much because when you implement a post processing effect, it helps you solidify like the concept of world space versus screen space because you can technically have some post processing effects that do use the world space information like depth to like um, create an effect. And then there's like screen space post processing effects, such as like your vignette effect, that just occurs um, on your screen, I guess. It's just limited. Its calculations are limited to screen space, I should say. Um, but yeah, it's also a really good way to like familiarize yourself with how whatever pipeline you're using, how it implements the render order or like the render queues. Before I mentioned how like post processing effects are generally like implemented last, and how transparents are, if I recall correctly, generally after your opaques. So yeah, I think that's like a really, really good task if you guys want to learn more. Procedural water is actually like a more challenging task in my opinion, depending on how deep you want to go with it. If you're like, there's a really good Acerola video on it if you want to learn how like games implement water. But if you want to dip your toes in like lighting techniques and understanding the importance of your normals, water reflects light, so that's like you need to keep that in mind. How water interacts with your light vectors will be a little different from like an opaque object. And because of the procedural movement of the waves, depending on how you're implementing the water, I guess, you generally have to recalculate your normals on the fly, especially with the procedural approach. And you also, of course, have to factor in that reflection behavior. There are other like considerations to think about when it comes to water, like that foamy appearance that appears in some waves. Like if you want to get realistic with it, procedural water shader, you can learn a lot from it. Okay, that's what I'm saying. Um, yeah, linking Acerola there. Acerola is a great resource. Okay, you should watch Acerola. And how to optimize shaders. So I already brought up how you can reduce the overhead with shader graph. Or you can reduce the overhead by writing code from scratch instead of like using visual scripting through things such as shader graph. Um, but I don't know. But there are like probably better optimizations you can do than that. I think writing it from scratch is um, it's always good, but like if you're unfamiliar with it, then you don't need to like go that neck deep into grass, I guess, or something. Whatever the phrase is. And yeah, this is like general advice from the Unity documentation, but it honestly applies to whatever you're doing. Truly, like avoid complex calculations, avoid repeated calculations, et cetera, et cetera. This is advice that kind of applies everywhere. So, and Unity has a GPU profiler for like determining certain metrics, such as like draw calls and stuff like that. I'm not sure if Unreal Engine 5 has a profiler like that, but I would assume yes, because it is Unreal Engine 5. It's a really good engine. So, and then RenderDoc is a tool you can use for really any engine and anything. It just requires some setup. But yeah, it's probably like the coolest debug tool. You can also use RenderDoc on games if it has an exe file. There you go. Okay. RenderDoc is like the coolest debug tool ever invented, in my opinion. If you're working with shaders, or especially if you're working with the rendering pipeline, I would definitely recommend getting familiar with RenderDoc. Basically, what it is imagine if you had like a visual artifact in your code or in your game, and you weren't sure what shader or like what was causing it. You can actually like screenshot that bug, and then you can click a pixel in that screenshot, and it'll show you the history of that pixel throughout the the graphics pipeline. And then you can basically like find out what shader caused it, where that bug is occurring in the pipeline, and it's just easy peasy. And it does more than that, but that's crazy to me, you know? That is crazy to me. It's actually crazy. But yeah, I guess that's all for now. I did want to like open up the Unity shader graph to like walk through like some like I guess practical application. But if you guys have any questions or want me to go back, where was the render doc 2 months ago? I'll send the by image. I got you. Oh, I don't know. Hold on. I'll send the by image later. I'll send the by image later. It won't let me copy and paste from the presentation right now. Okay, I'll pull out the snipping tool. But yeah, let me actually switch my screen share real quick. Actually, let me close it because I have my Visual Studio up and I have my SQL server up, and that might show some things I don't want to show, like API keys. So let me close those real quick.
Wait, Daniel, I have a question.
Yes.
I'm curious, when it comes to, I guess, like imagine like you're someone that's learning shaders for the very first time, like how early on do you think like you should do, I guess, a deeper dive into the graphics pipeline to help like I guess further your understanding when it comes to making shaders? Or like I guess how important or how early do you think you should start learning? Like deeper than what you just shared with us?
It really depends on what you want to do with it, right? Because, like I said, like the graphics pipeline stuff, like those deep dives that I talked about, like regarding like you figuring out how normal mapping works in like the context of like setting it up within a graphics pipeline. This is like stuff like generally you're gonna see graphics programmers doing, like working on those pipelines and stuff. But like for tech art, I don't know if that holds the same level of relevance. It's still useful, don't get me wrong. But like, because like for me, I learned those APIs first before learning shaders, and my shader skills still need a lot of touch up, right? So like, if you want to like, and there's a lot of things to even learn even within shader land, right? Like I brought up like fractional Brownian motion, which I didn't actually discuss it. I forgot to, but fractional Brownian motion is basically a noise algorithm that lets you, use to generate like procedural land generation or things like procedural water. Um, and that's like just one category of things, just like algorithms you can use within your shaders to create cool effects. And there's like a million other effects, like uh, like post processing effects, like screen space ambient occlusion and all this other cool stuff. Or like the Fresnel effect, right? Which is usually built into uh, game engines, like for shader graph and stuff. But yeah, I mean, basically, my answer is if you just want to make shaders, I think it's more useful to understand those, I guess, techniques. Yeah. So like those things I listed, like FBM for now, those are techniques. Okay. And I think as a tech artist, it'd probably be more useful to familiarize yourself with those things than like taking deep dives on how to implement a pipeline, for example. But I think learning the graphics API, if you have the free time, I think that would be really useful in furthering your skills, improving your skills even further in terms of like how to optimize these algorithms, how to write good shader code. how to make sure that like it'll also help you debug um, bugs related to your shaders as well. Because if you see a visual artifact related to your shader and you don't know why it's happening, well, understanding where the bug is occurring in the pipeline and knowing how to use RenderDoc is really useful too. Um, so as a tech artist, I would recommend learning those how to implement the shaders first. And then once you get to a comfortable level where you're familiar with writing visual scripting and then shader code as well. And once you've familiarized yourself with it doesn't need to be all the techniques, but like a good chunk of them, then I think it'd be worth like taking a deep dive into like graphics programming. But I think at the minimum, definitely understand how the graphics pipeline works, um, at least at a high level. That's why I brought it up. But like, you really don't need to be learning Vulkan, right? Learning Vulkan is like super complicated. So yeah, you don't need to be learning Vulkan unless you really want to. But like, if you're just writing shaders for fun, it's not too necessary. Um, but yeah, I think that'd probably be my answer. Basically a mixed answer. On an unrelated note, brownies are delicious. You know, I actually cooked brownie cookies about 2 days ago, and now they're quite stale. But I'll still eat them with milk. So I agree with that full heartedly. And yeah, I mean, I guess for the remaining like time we have um with what we have, we can play around with shaders. So this is Unity shader graph. I already went over it like 1,000 times, but I'll show like one aspect of like the vertex shader that I have shown here, right? So like this is a really bad algorithm to do, but like um because it not because it's like not performance, but like it's just kind of ugly. So if I do this, and I'll explain in a second, I passed in this like vertex displacement manipulation, and it did nothing because the value is, I believe, set to 0. Give me a second. Yeah, so like notice how by like I can displace the vertices with this this input I have here. And I would actually be careful with like using this kind of vertex displacement manipulation because it can go wrong. And it can cause bugs, for example. So like if you see our tree here, you see the size of this like leaf mesh here. Um, so like if I bring my screen down, okay, and it's still barely visible, right? But if I increase it, okay, you'd expect it to be still visible. But if I bring my screen down, it disappears in view, which is like unexpected behavior that you should watch out for when working with like vertex displacement. I don't know if this is like exclusive to like the Unity engine, but it is something you have to worry about Unity at least. So yeah, just be careful about that. Um, and the way how this works is I basically add um, this position with like this noise sine wave node graph or node here I have, right? And it doesn't necessarily need to be like, oh actually no, I'm inputting it into the noise sine wave, and then the noise is I guess affecting our position input. But you can actually like do a bunch of other stuff, like you can size it up with multiply, right? So like if we go to our scene here, I'll say real quick. And let me put this at 1 real quick. So like it's small, and then we do like this, and now it's tall. So yeah, I mean that's like one example of how you can manipulate your vertices to do cool effects like that. For the fragment shader, I have like a basic like Fresnel effect here. Fresnel effect is like probably like really cool, but I have this base color here. If you notice here, I'm passing in like a base color into the base color node here. And we can use this color to like manipulate the color, of course. So very basic stuff. And if you remember the emission value, so I'll show you what it means by like glow effects, right? So we pass in the emission. Um, we pass in the value into the emission using this Fresnel effect, and it now has a glow. which is really cool. Um, and another cool thing I'd like to show is if we use a float value, right, like 0, pass it into our normals, what happens? Lighting doesn't work anymore. So this is what I mean by your normals are really important. Um, yeah. All right. I think that's probably like my basic like workshop as far as like presentation goes. I don't want to go too deep into the shader stuff because good shaders take a while to make. But this is like basically how things work on a high level. And if you guys have any questions, I'm open to it. Um, oh, here we go. Okay, do you have an example of the CPU being better for processing something over the GPU? A good example. From the rendering side of things, I don't know. Because like I said before, the graphics card or the GPU was designed with graphics in mind. So it's hard to find an example in like the graphics realm of things, but there are some advantages the CPU does have. I think generally speaking, it's if you're working with like a small amount of data, like for example, like oh man, I'm not a gameplay programmer, but I think a lot of gameplay programming it does happen on the CPU side of things. Um, because more processing speed, so like you can make those, I guess, physics calculations sooner, um, and you're not working with as much large amounts of data since you're really just like making like a physics calculation here and there. But if you're working with like a large amount of like information and you want to do like physics calculations still, well, the GPU well, a compute shader could be better for that. Like for example, like a physics based particle system. Um, it really just depends on how much. It depends on your use case, right? If you're working with a small amount of data that needs like an immediate response time, your CPU is generally like your friend. And if you're working with like a large amount of data, um, where you still want a good response time, but of course it doesn't need to be like as immediate compared to like the CPU, then I mean it's still pretty freaking fast. I mean it's a GPU, right? So it's still going to be fast, but um and if you're doing matrix multiplication, that's another thing. The way GPU handles matrix multiplication is kind of different. I actually have a video linked in the speaker notes. Let me actually link it real quick. Um, let me find it real quick. The compute shader, here it is. Okay, so um, um I'll link the video later, but I can't find it. But it's somewhere in the speaker notes. Basically, the GPU does matrix multiplication really, really well. Okay, because it can subdivide the I guess operations within that I guess matrix multiplication within like like a number of threads. There's a whole like NVIDIA like I guess website on it. Like I said, I'll link it. I this is like out of my depth. When it comes to like the details of GPU architecture, it's honestly out of my depth. It's a really complicated topic. Um, when will we successfully write an algorithm that turns stale brownies into fresh brownies? I'm waiting on that as well. If you let me know if that exists, I'll be using it today. So, can you explain why the vertex shader is often faster than the fragment shader? Um,
I can explain
um,
this. This is just
yeah, yeah.
a question I was asked in an interview for graphics, and I thought it was really good for people to know.
But before you explain it, can I guess?
Yes.
Okay. My guess would be you're dealing with raw input data instead of the fragments. That would be maybe one factor. The other factor is that maybe it has an advantage of happening sooner in the pipeline. If that would be my guess. But yeah, those would probably be my two guesses. What was the real answer, Henry?
So whoever is overcast actually nailed it. Um, the correct answer is because the vertex shader operates once per vertex, whereas the fragment shader operates once per pixel. And for almost every situation, unless you're using a mesh with an ungodly amount of vertexes, there's usually far more pixels on the screen than there are vertexes on the screen. So if you do an operation on a vertex shader on like a cube, that's only running 6 times for each vertice. Um, Whereas, or I guess it would be more, not necessarily points, but you'd be running it a whole lot less times than however pixels are on the screen that make up the cube, if that makes sense.
Can we get the clap sound for that? Whoever was running that.
That was me, so I will clap for myself.
What is the difference between a programmable and fixed stage in the graphics pipeline? So fixed stages, remember the rasterization stage. Those are fixed stages, as in like you can't change them. They're meant to do like one thing, which is to rasterize. Well, in the case of the rasterizer stage, you're rasterizing the raw vertex data into fragments, soon to be pixels. I think there's a difference. Maybe there's not, but I do think they do differentiate between fragments and pixels, if my memory serves correctly. Don't take my word for it though. And your programmable stages will generally be your shaders. If you guys remember the whole Vulkan pipeline I showed, it had a bunch of shader stages, like the mesh shader. Those are like programmable. Do you know if there's a way to add your own shader nodes or take code you wrote and somehow translate that into Unity, then into a shader node? I wish Nathan was in this call. Okay, I know you can make subgraphs, so you can make shader nodes. So you can make shader subgraphs and then reuse that subgraph in another shader graph. But I don't know if you can write your own shader node in the context of shader graphs. I think you can do this. I know you can do it with VFX graphs where you can write your own function and then implement it into the VFX graph. I'd have to Google that. Let me check. I feel like it should be possible because there are extensions like Amplify, and why would they not make a custom? Okay, I'll have to get back to you on that. This is gonna the custom function node lets you inject your own custom HLSL code in shader graphs via the Unity documentation. So yes, that is possible. And you can also make subgraphs with shader graph as well. And fragment shaders are usually for colors, while vertex shaders are for moving the shape, right? Yes, correct. Generally speaking. Maybe there's some exceptions, but yeah, generally speaking. I don't know about Unity, but you can definitely do that in Unreal with a custom node. I think that is good for other people to know. I was asked in an interview and had no idea. Yes, that is an important distinction to know. I think there's a way to create. Man, I am moving at slow-mo compared to you guys. Yeah, subgraphs. Yeah, in Unreal, you also get that weird mesh disappearing. Okay, yeah. So in Unreal, you have to worry about the weird mesh disappearing thing with vertex displacement. So yeah, just be very mindful of that. Because I was actually playing Battlefield 4, the campaign, and I actually noticed that bug in the campaign where a sign fell down, and whenever it was out of whenever I viewed it out of its original position, it just disappeared suddenly. So it even happens in AAA games, believe it or not. Do the shaders stop being applied when they're no longer in the screen space? It depends on the shader. Well, and this is a complicated thing. I'm not. It depends how you interpret this question, right? Because technically, shaders are always being applied. It's just the pixels are being overwritten depending on like the order of your shaders, right? So like, yeah, I mean, they're still being applied, but like the end result really like, okay, for example, like if I have this tree, for example, if you're still watching my stream, I have this tree, I pass in this shader that I already have written, and it turns it gray. So this is still going on no matter what in the render pipeline. And then if I make a post-processing effect that is in screen space, it's going to affect every single pixel on the screen. So it's still being applied. It's just being overwritten and changed by like a post-processing effect. Maybe I misunderstood the question, but when they're no longer in the screen space, okay. I think it probably depends on. I'm not sure. That's a good question, actually. I think I now understand it because yeah. So I think it's because the object gets cold when all of its non-display verts go off screen. I wonder, does calling behavior stop shader scripts? I don't know if that happens. I know objects get cold, but I don't know if the shaders like stop running. Let me check. I mean, I feel like that would make sense. Why would you not make that optimization, like in your pipeline? Do shaders stop executing when the object is cold? I'll Google it right now. I'll do some learning myself. Okay, this is going to take way too long, but you know what? If I find an answer, I'll let you know. Calling a CPU shaders happen after, I think. CPU probably doesn't have access to positions of displaced vertices. Most likely not. Yeah. Oh, you know what? That actually makes sense. That's a really good answer. So just for the video, I'm going to repeat what's going on in the chat. So before I mentioned this weird calling behavior that would happen with, oh geez, okay. That's right, I changed the code. All right, but anyways, whenever the, I'll just change, what am I doing? Okay, I'll just reconnect the nodes. Okay, and then I'll talk about it. Let's freaking go chat. All right, so just for the video, this is all overcast. This was a great freaking answer for why this calling behavior happens. So essentially, since calling is typically defined on the CPU, well, maybe not calling, but like the camera, right? Like the projection matrix and stuff. So like since calling happens on the CPU, the displaced vertices or the original vertices. So let me bring it up. Yeah, so like these vertices are like the original vertices that you kind of see in that like CPU to GPU round trip where like the CPU sends in this object data and then the GPU interprets it. I'm not sure if this happens in the Unity pipeline, but I mean it's what I learned in learnopenGL.com. So I'll just use that as an example. So assuming what I'm saying is correct, let's say the CPU sends in this vertex data to the GPU, and then the GPU transforms this data. Well, since the camera is on the CPU side of things, the projection matrix, it doesn't have access to these newly transformed vertices. So it's just going to assume that they're no longer there and it's going to call them. So yeah. Good answer, Overcast. Even I learned something every day. Can you explain calling for those here that might not know what it is? Yeah, so calling, I'll actually draw it out, to be honest. It's easier to draw out. Okay, actually, I don't even think I needed to end the stream. Sorry. So calling is, so you have your camera, right? And if you remember if you remember when I talked about the projection matrix with the vertex shader example I brought up, the projection matrix it makes a multiplication operation to, I guess, convert it to screen space, right? And your projection is essentially, I mean, it's like predefined, right? It's what you want it to be, but your projection will be how your camera, I guess, looks, more or less. And outside of these bounds, right, just these black lines, um, outside of these black lines here, all of this stuff gets cold. So everything that's like outside of the camera gets cold. And that's more or less how it works. It's pretty simple, but there are like a few caveats to understand. There's actually a lot of forms of culling. This isn't the only form of culling, right? So yeah, this is for some culling related to the camera. And in this form of culling, we have like this near plane. You can actually define a near plane as well in this far plane. Let me use the black paints here. Oh, you know what? We'll use green. Green is a little cooler. Okay, so we can define a near plane and a far plane, and everything behind this near plane will get also cold, and everything after this far plane will also get cold. So like it's like an additional optimization you can consider if you don't want to render like really far objects. Another form of culling that I actually got asked in a Blizzard interview is other forms of culling. Like what are some other forms of culling, right? And something you don't really think about often, and that's really just a big optimization in general, is backface culling. So like if you have a cube, and I'm not, yeah, here we go. If you have a cube, well, you don't really need to render each face. Like you don't need to render behind this face, right? So that's what backface culling is. You're only rendering the front of the pixel, which is really nice. There are some aspects where you don't want to do backface culling. Like if you have like a cape where you do want to render both sides of that object, then you'll want to do front and back face. You'll want to render both the faces. What would be the reason to cull close to the camera? Cull close to the camera. There are a couple of reasons. It this is gonna get a little complicated, but there's this algorithm called shadow mapping, and it's not necessarily the same as a camera, but basically how shadow mapping, oh god, this is way, I can't explain this right now, but there are some aspects, I'll just keep it vague. We'll just keep it vague. Shadow mapping is a complicated topic that I can't really explain right now. I have to really double check on what I'm saying. But there are some algorithms that benefit from cutting away certain noise near the camera, I guess you can think of, or like near the projection, or the where you're projecting from. So you could get some, like, I guess, bugs if you don't do this early culling. I'm not sure if that's the best way to add it, but there are some use cases for that. Some other use cases could be like, okay, maybe you don't want your player's model showing when your camera is like right next to it. So that's like one example. Let me actually look up shadow mapping real quick for Unlearn OpenGL, and then we can walk through this together. Um, wow, this is really complicated. All right. Okay. So basically, how shadow mapping works is imagine the light being a camera, right? We're projecting a ray from it, and then we're basically calculating what cameras are, or what is in shadow in respect to our, I guess, light perspective. And that's kind of more or less how shadow mapping works. It uses a light projection, and this light projection has a near plane defined, and there can be some benefit to increasing the light plane, the near plane of the light projection, if you're getting like shadow artifacts. It's not always the case. Sometimes it's not that big of an issue, but there can be some benefit to it. So that's like one case. And yeah, if you want to learn more about shadow mapping, you can do like I'll link it. You can do a brief read if you want. So And this is once again more graphics programming side of things. You're generally not going to be setting up shadow mapping because this is kind of handled by the game engine, by the graphics pipeline. So shadow mapping is not something you generally have to worry about, but it's still fun to learn. So um, no more questions. If anyone also wants to like share any cool like factoids about like shaders, feel free to like unmute and mention them. I think that's cool. Oh yeah, we did hit 8 p.m. We did hit 8 p.m.
Yeah, Daniel, I guess unless you had any other specific things, I think we should all say thank you, Daniel. Yay, do the golf clap.
Oh,
Discord sound.
I'm glad you guys learned a lot. Let me. You guys should also. Yeah, I'll link the slides right now. You guys should also. Oh yeah, there's actually a bunch of resources in these slides. We have a bunch of resources in these slides. You can learn a lot about. I have everything linked. Everything I spoke about is sourced either in the slides or in the commentary speaker notes. Everything is linked. Okay, absolutely everything. And I even credited all the cool shaders people made. Maybe you can check out those things as well and learn something from it. There's a lot of good like I guess commentaries on people shaders that they made. But yeah, you can learn so much. And if you want you know if you want to take a deeper dive, definitely check out the resources I have listed. Okay. But yeah, feedback form, please fill out the feedback form. I think like I know we didn't go over a workshop. Maybe if you guys wanted more interactive. I know I wasn't as interactive as I'd really hope to be honest. But um any suggestions on how to handle more interactive, I guess, interactiveness in these workshops would be nice. Maybe a Kahoot or two. I don't know. Let us know. Let us know. I freaking love Kahoot, man.
We'll also post this feedback form in a more visible place than the voice channel chat for